Hello everyone, this PowerPoint is going to cover Chapter 3 of the textbook on perception. So Goldstein, your textbook author, defines perception as the process of recognizing, organizing, and interpreting information from our senses. He makes the point that perception is best thought of as a process like reasoning or decision making. That is, our perceptual system is constantly reinterpreting the information that is available to it to try to make sense out of the environment. The example he uses is of a woman named Crystal jogging along the beach. While Crystal is jogging, she notices an object about 100 yards ahead of her that wasn't there yesterday. She thinks to herself, what an interesting piece of driftwood, although it's difficult for her to make out the object clearly. As she gets closer, though, she realizes that it isn't driftwood at all, but an umbrella that was lying under the lifeguard stand yesterday. This demonstrates a couple things about perception. First of all, it demonstrates that perception is based on the quality of the visual information. When Crystal is far from the object and cannot see it very well, she has difficulty recognizing it. But as she gets closer and can see it more clearly, her perception of the object improves. It also demonstrates that perception is affected by one's knowledge, expectations, and memory. What helped Crystal ultimately recognize that the object was an umbrella? Well, she remembered seeing an umbrella at that point on the beach the other day. So again, she used her memory and expectations of the type of objects that usually appear at that beach to correctly recognize, to perceive that object. Another point I want to make about perception, which I hinted at in the Chapter 2 PowerPoint, is that perception is not about making an exact copy of objects in the environment. Think back to our square example. We had two squares, one on the top and one in the middle of the grid, and the question was which square looked darker. Everyone says that the top one looks darker, but as we saw in the Chapter 1 PowerPoint, they're actually the same color, the same shade of gray. The reason we perceive them to be different colors is that our perceptual system doesn't just make a copy of objects in the environment. Instead, it compensates for the middle square appearing to be in a shadow, and so we perceive the square to be lighter than it actually is. So again, perception is about recognizing, organizing, and interpreting information from our senses, not about making an exact copy of objects in the environment. Another thing I want to do is to talk about the difference between bottom-up and top-down processing. Bottom-up processing refers to processing that starts with stimuli in the environment activating one's sensory receptors. We might ask, for example, how do we see objects in the environment? The quick and dirty answer is that light reflects off of objects in the environment, and that light falls on our photoreceptors, which are our sensory receptors for vision, located in the retina of our eye. This information is then sent to our brain, and different parts of our brain process information about the shape, color, motion, etc. of the object. So, this is bottom-up processing, processing based on stimuli in the environment activating one's sensory receptors. We can contrast bottom-up processing with top-down processing, which is processing that starts with one's knowledge or expectations. For instance, remember how Crystal ultimately recognized that object as an umbrella. She used her memory of the objects that she had seen in that part of the beach before. Specifically, she remembered seeing an umbrella near that location a couple of days ago. This is an example of top-down processing, processing based on one's knowledge or expectations. Now, this distinction between bottom-up and top-down processing can be difficult to understand, so let me go over a few more examples. Here's an example that Goldstein uses in the textbook. If I ask you to identify this object, you would probably say something like, it looks like a dark gray blob to me. That is, you'd be able to describe its visual features, but it probably doesn't look like an actual object to you. However, what if I put it in a scene or context? Here, that object might look like a soda can. Here, that object might look like a shoe. Or here, that object might look like a car or a fire hydrant. So what this example demonstrates is the effect of top-down processing on perception. In each example, the bottom-up information is the same. You see the same exact blob in all scenes, so the visual information is the same. What differs, though, is the top-down information or the context of the scene. And your perception of the blob changes as the context changes. That is, you recognize it as a different object in each scene based on the types of objects you expect to find in that scene, based on your knowledge of the types of objects that are usually found in that type of scene in that location. Here's another example based on a class demonstration that I do. What I do is split the class in half and have the students on the left half keep their eyes open while the students on the right close their eyes. I show the students on the left these three symbols and I ask them to identify and remember the middle one. I then have the students on the left close their eyes and the students on the right open theirs. I then show the students on the right these three symbols and have them identify and remember the middle one. Then I have everyone open their eyes and I have them nod their heads that this was indeed the middle symbol that they all saw. And then on the count of 3, I have them yell out what they think this symbol is. The students in the left half of the room yell out 13, while those in the right half of the room yell out B. So I say something like, wow, you guys are all intelligent college students, and you can't agree on whether this is a 13 or a B. What's going on? Well, this is showing the effect of top-down processing. Even though the bottom-up information was the same for all students saw the exact same symbol, the top-down information or the context differed. Those who saw the symbol surrounded by numbers perceived it to be a 13, while those who saw the symbol surrounded by letters perceived it to be a B. So again, this shows how context and expectations can affect perception. Next, we're going to discuss a specific task in perception, object recognition. Object recognition refers to the process of identifying complex patterns or arrangements of sensory stimuli that are different from the background. So in the crystal example, object recognition would be when she ultimately correctly recognized that object as an umbrella. We'll begin by talking about different facts about human object recognition. The first fact is that object recognition is extremely fast. So let's do a little demonstration. First, I'm going to give you a type of scene. Then I'm going to show you a series of pictures presented at a rate of about 3 pictures per second. And then finally, your task is to yell out when you see that scene in this set of pictures. So make some sort of response when you see the picnic scene, and again, keep in mind that these pictures will come quickly. So here we go. So again, you're looking for a picnic, make a response when you see the picnic scene. So, you probably had no difficulty recognizing the picnic scene, even though each scene was only presented for about 1/3 of a second. This demonstrates that we recognize objects pretty quickly. The second fact is that people can recognize objects that they have never seen before. So you've probably never seen these exact cats before, and you've probably never seen a cat trapped inside a birdcage before, but you're still able to, oh, he just looks so cute, but you're still able to recognize all of these objects as cats. Similarly, when a new iPhone comes out, nobody says, oh, that's a cool looking microwave. People recognize it as a phone right away, even though they've never seen a phone that looks exactly like it before. Third fact is that people can recognize objects even when the bottom-up information is poor. For example, people can easily recognize objects that are partially occluded or blurred. In this first example, many of the objects like the book, the pencil, and the scissors are partially occluded or partially covered by other objects, but still you can recognize those objects just fine. Similarly, here are some blurry photos of famous people, and despite the fact that the pictures are blurry, you can probably recognize the famous people without too much trouble. So, what this demonstrates is that even when the bottom-up information, when the visual information is poor, when you don't get a perfect look at an object, you can still recognize the object fairly easily. The final fact is that people exhibit viewpoint invariance, which is the ability to recognize objects seen from uncommon perspectives. So normally when we see a chair, we see it from this first perspective. Well, when I show you this chair from this perspective or from this other perspective, you still don't have any trouble recognizing it as a chair. This is what I mean by viewpoint invariance, that you can recognize objects from perspectives or viewpoints that you don't usually see them from. Similarly, the most common or canonical perspective of a horse is one of these pictures in the top row, right? That's the perspective we usually see horses from. But even still, you can recognize the objects in the second row and the third row as horses, even if it takes you a little longer. So again, this shows that humans are good at recognizing objects seen from uncommon viewpoints or perspectives. The last topic I want to discuss today is a specific theory of object recognition known as recognition by components theory, or RBC theory for short. The logic behind how humans recognize objects according to RBC theory is similar to how humans recognize words. So according to RBC theory, objects are composed of arrangements of simple three-dimensional shapes called geons, and we recognize objects by perceiving their geons. So Think about how humans recognize words. Humans can recognize over 150,000 words in English using only 26 different letter combinations presented in different arrangements. RBC theory says that something similar takes place in object recognition, that humans can recognize a variety of different objects using 27 geons in different arrangements. For example, here we see several different geons on the left and how those geons can be arranged to form different objects on the right. And again, just like with word recognition, different geons and different arrangements can be combined to form different objects. Now, there are two important properties of geons. The first is that geons can be recognized from multiple viewpoints. That is, let's consider the geon on the third row down that sort of looks like a cylinder. The point here is that we can tell that that geon is a cylinder at many different rotations. The same is generally true with the rest of the geons you can see on the right there. It's not perfect, and the geon might look a little different at different rotations, but you can generally recognize them from different viewpoints. So, the question is, why is this important? Why is it important that geons can be recognized from different viewpoints? Well, like we talked about over the last couple of slides, humans show viewpoint invariance. People can recognize objects from different viewpoints. And so, if RBC theory is correct, that we use geons to recognize objects, it must be possible to recognize those geons from multiple viewpoints. The second important property of geons is that geons can be recognized even when they are partially occluded. So you can still recognize a part of a cylinder geon as a cylinder geon if you can only see a small section of it. Again, this is important because humans can recognize partially occluded objects, and so if RBC theory is correct that we use geons to recognize objects, it should be possible to still recognize the geons even when they are partially occluded. To put this all together then, how does object recognition take place according to RBC theory? So according to RBC theory, object recognition involves matching an object's geons with the type and arrangement of geons stored in memory for the objects we know and are able to recognize. So the first step is to identify the geons used to form an object. A cat, for example, might be comprised of these geons in this arrangement. So to identify an object, we must first identify the object's geons. RBC theory claims that for each object we can recognize, we have the arrangement of that object's geons stored in our memory. So to identify this object, RBC theory says that you compare the geons for this object to the arrangement of geons for all objects you're able to recognize, the ones you have stored in your memory. Ultimately, one of those arrangements, presumably the arrangement for cat, is going to be the closest match, leading you to recognize this object as a cat. So the object in memory with the closest match is identified as that object. Next, we're going to look at evidence to support RBC theory. The first piece of evidence is that the more of an object's geons we can see, the easier it is for people to identify that object, suggesting that we are using geons to recognize objects. So remember, RBC theory says that we recognize objects by breaking them down into and then recognizing their geons. It would make sense then that if geons are important for object recognition, that the more of an object's geons we can see, the easier it is for people to identify that object, suggesting that humans do actually use geons to recognize objects. In one study, for instance, the more of an object's geons people were shown, the more likely people were to recognize that object. Right? We might not be able to recognize this as a plane if we only see 2 or 3 geons, but the more geons we see of this object, the easier it is for us to recognize that object. Here's another example. Try to recognize this object. Okay, I'm guessing you're having difficulty doing so. Now try to recognize this object. And hopefully this one's easier for you. You can recognize it as a flashlight. The point is that in both of these images, the same total amount of the object is available to be seen, but in the image on the left, the object's geons are obscured. While on the image on the right, you can see what the object's geons are. So again, hopefully it was easier for you to recognize the image on the right as a flashlight than the image on the left, presumably because you could see more of that object's geons, leading to successful object recognition. The next piece of evidence to support RBC theory is that object recognition is easier when an object is seen from its most common perspective, the position its geons would be stored for, but it's possible from other perspectives that still display the object's geons in that arrangement. So remember, the way we identify an object is to break the object down into its geons and then to compare the arrangement of those geons to the ones stored in memory for the objects we know. The perspective we store an object's geons for is the most common perspective that we see that object from. In the horse example, maybe it's based on the viewpoint shown in the image on the top left. The point, though, is that for most of the other perspectives, the arrangement of the horse's geons is very similar, and so RBC theory is able to explain viewpoint invariance. As long as we can see the object's geons and they are in the same arrangement, we should be able to recognize the object correctly, which we can in all of those other horse examples. When you can't see the object's geons, though, things get tougher, which is, understandable. If you can't see the object's geons, it would make sense from RBC's perspective that you'd have trouble recognizing that object. But here's a good example of that. You probably have no problem recognizing this item as a blender, right? This is the perspective that you would normally see blenders from, and so it's the perspective you would have, the blender geons stored for. However, if you see the blender from this perspective, you might have trouble recognizing as a blender at first. Again, this makes sense as the geons you see from this perspective are much different than the ones you see from the original perspective, again, the perspective that you would have stored the object's geons for. The last piece of evidence to support RBC theory is that different objects composed of the same geons can be recognized as being different based on differences in the arrangements of their geons. So, think about word recognition for a moment. Humans can differentiate between words made up of the same letters as long as the arrangement of those letters is different. Take a look at the words like star and rats, right? The letters are the same, but because those letters are in a different arrangement, it makes them different words, and we can recognize them, correctly as different words. The same thing is true in object recognition. In this example, we can see that a mug and pail are formed by the same geons, a straight cylinder plus a curved cylinder. But in these different objects, the geons are in different arrangements. In the mug, the curved cylinder is on the side, and with the pail, the curved cylinder is on top. So again, RBC theory correctly explains that people should be able to tell these objects apart, even though they are made up of the same geons. Because the arrangement of the geons is different, we can identify them correctly as different objects. This brings us to a couple problems with RBC theory. The first problem is that the global shape of an object may be sufficient for object recognition or more important than the object's geons. So again, RBC theory says that the way we recognize objects is by identifying the object's geons, but here's some evidence that no, it's possible to recognize objects even when we can't see their geons. For example, we can recognize silhouettes of objects just fine, even though we can't necessarily see the object's geons. Or in this example, if we look at the top right object, the object in the unnatural disconnected condition, even though that object's geons are sort of being, manipulated so they're not intact, we can still recognize that object as a car because the global shape is the same. So again, the global shape of an object may be sufficient for object recognition, or maybe even more important than the object's geons, whereas RBC theory would say that no, it's all about the geons. Another problem with RBC theory is that it can't easily explain how we can tell objects apart that have the same type and arrangement of geons as other objects. A couple slides ago, we saw that if the geons were the same, but the arrangement of the geons was different, it was possible to tell the objects apart, such as with the coffee mug and the pail. However, if the type and arrangement of geons is the same, then RBC theory should say that we would not be able to tell the objects apart. The issue, though, is that humans can tell objects apart that have the same type and arrangement of geons quite easily. Think about animals like cats, dogs, foxes, and wolves. Their arrangement of geons would pretty much be the same, right? They would basically look like that. And so, RBC theory would predict that we would be unable to tell these different animals apart, but clearly we can do so quite easily. This suggests that RBC theory is incomplete and that object recognition probably does involve more than simply identifying the object's geons. Anyway, that's all I have for you guys today. Have a great week, and I'll have more PowerPoints for you next week.